we'll be doing some Q&A, and I'll be starting with some questions, and then we'll bring in some audience questions as well. Since we have two Bobs on the line here, I think I'll try to direct the questions by company so that we don't get too confused. So I want to start off with GSI, and I guess either you guys can chime in as appropriate. But just to clarify, you said that the Gemini and the Leda card are shipping now. Is that sampling or is that full production?
It's not full production yet, but yes. So I guess it's sampling. It's the correct.
Okay, and when do you expect the production to be ready?
First half of next year. Great.
And then what kind of applications are you guys seeing, for this technology? I mean, you showed a few algorithms that it could be used for, but what kind of customers should be interested in this?
Dan, you want to take that one? Go ahead.
Sure. Okay, so first it's a programmable processor, right? And we think it can target multiple application domains. And clearly, the first one we're looking at is search, being a very suitable search processor capable of doing all kinds of searches, starting from similarity search, which is not exact search, and ternary search, which is unique for a processor. And this can basically complement also AI functions, algorithms, and applications, but not limited to search. So this is why we want to showcase basically the capabilities of the technology and not just for a specific application.
Okay, and just to clarify, when you say search, I mean, you're talking about like taking a big database and then being able to go through that and look for a particular item or a particular configuration of items that and find that very quickly, right?
Right, finding it very quickly, especially when data is in memory, that's done instantly almost, and also at a low power. So basically, when you're looking at the combined performance, which means latency per query and power per query, then it becomes highly competitive.
And you mentioned AI, but when you're talking about AI, are you talking about doing a complete neural network, or you're talking about doing some piece of the neural network?
We're talking about basically converting some AI problems into search problems, which means that some inferencing problems, for example, are done by running the samples, the signals through some neural network, and that can be done anywhere in the data center or by the actual application itself, and doing basically the inferencing or the search within the associative memory.
Okay, so this wouldn't be applicable to any AI problem, but just certain specific ones.
Yes.
Okay, right, that makes sense. And you mentioned this is a programmable processor. So what kind of software tools are you providing to help with the programming?
So right now we offer libraries in the function libraries, and we have a simulator, a core simulator. So we're able to simulate the code and debug the code, etc., on a desktop, server, whatever. And later on, we'll provide a compiler, so you can start with a high-level code and get your associative code.
Great. So I wanted to ask GP a couple of questions. So GP, you mentioned that the chip is able to scale down to very, very low power, 80 microwatts of operation. How much AI performance or GOPS or whatever can you achieve at that very low power? And then what kind of neural network function would you be running there at that very low power?
So in that, we are able to do the audio phrase or keyword spotting, where the audio is sampled as 20 kilo samples per second. It's pretty fast sampling rate. I do not remember exactly GOPS number there, but we are running a GRU network, an LSTM network, to do this phrase or keyword spotting at that power consumption.
Okay, so that would be the application for that low power. And then when you turn on all the engines at the full clock speed, you said you can get up to 512 GOPS, right?
Correct, sir.
Okay, so about about half a TOPS, and so you mentioned that this chip can do training as well as inference. Now, I mean, most training, pretty much all training today, seems like is done in the cloud. So I wanted to understand kind of what scenario or what application you're thinking of where you would do training at the edge. Is that like more of a retraining sort of scenario?
Correct. That's the application we imagine will happen in these devices. Let's say you want to train the weights for different type of dialects in a country for wake-up word or natural language processing. Then that type of retraining can be done on the device itself. One doesn't need to go to the data center. Similarly, if the sensor behavior shifts, whether in industrial or even audio microphone behavior shifts for audio type applications, this device will be able to retune itself to those changing conditions. Another place where it will get used is a lot of self-healing, where the weights degrade or the model degrade over time. You'll be able to tune it as a lot of adaptive training or self-healing, as it is called, will be able to do using these. And that's where we also see a lot of traction, that people are very attracted to this type of concepts and technology.
Great. Thanks, GP. So for Untether, so Bob, the performance you guys are getting on some of these neural networks, what batch size is that?
So we're all batch equal to 1. That's what our chip is architected for. We do that to minimize latency, obviously, and that's what people are looking for the majority of their inference workloads.
Yeah, that's really impressive, because some of these other chips need much larger batch sizes to get up to the peak performance that you were showing. So even with the 4 chips on the card, you can operate at batch size 1?
Yes. So for example, like with BERT base, we actually split that between 2 chips. And then we have the head of another BERT starting on that 1 chip and split that between chips. And the banks can directly talk to each other, obviously, because it's asynchronous in terms of going through the pipeline bus to the PCI Express. So that's how we do it. We also can put multiple networks onto a single chip. And sometimes we'll replicate those networks multiple times and have them all run in parallel and just do a multi-stream type of approach, each of them running batch of 1, but running different networks.
Okay, that's pretty cool. And then you mentioned that the software can extend models across even multiple cards. So in that case, would the batch size expand, or you still able to partition the model finely?
Yeah, we still partition the model, do the graph separation, and do part of it in chip. Through PCI Express, our runtime takes the data and then moves it to the next card and the chip on that card where the graph has been split to.
So I brought these 3 talks together because, the similarity between keeping the compute and the memory together, kind of minimizing the power to move the data around. But I mean, Bob, at Untether, I mean, you talk about an at-memory architecture versus an in-memory architecture. So you're kind of messing with my theme here. Can you talk about what the difference that you see between the at-memory and the in-memory are?
Sure. So the at-memory is obviously all digital, right? We have a digital processing element directly connected to the memory array. Okay, but the memory is not doing the actual compute. In memory architectures, you're trying to use the memory cell to actually do the multiply, use Kirchhoff's law, as was described in the other presentation, to do the accumulate, to give you that similar multiply accumulate, but you're doing it all in the analog domain with A to Ds and D to As. We like our structure just because it's all digital, CMOS logic, manufacturable at scale. As you heard GP talk about, he does a lot of work trying to optimize to remove the noise, the variations of PVT, those types of things. You know, if you're using flash cells, you have to have a multi-level cell. You can have drift, charge loss, those types of things. So for us, we went to the architectural innovation, not the process innovation.
So GSI, can you guys talk about? I mean, you're actually pushing the compute into the memory. I mean, what are the advantages that you see there versus just putting compute cells next to the memory?
So, Linley, if I may, with due respect.
Oh, okay.
Actually,
Well, let GP jump in first.
yeah, actually, look, I mean, I will be willing to debate this as long as time may take. I'll be willing to debate this. In-memory computing and the concept of putting this devices, this Mac, very close to memory is actually a very flawed concept, as a matter of fact. The reason is that when you make the memory size very small, the power efficiency actually become worse. So if you go down to the memory design itself, this whole concept that I am putting my multiply accumulate very close to where the memory is, actually it doesn't work very well. We have tried this for a very long time. So unless you, I mean, yes, it is just a partitioning type of partitioning exercise where you say, okay, I'm going to take this much memory and put this many multiplier adds next to it, and I'll be dispersing these operands all the time. The problem with it is, and as I said, I will be willing to debate this for as long as it takes, is that when you make the memory small enough, the efficiency actually goes bad. It becomes worse. And then now feeding into that memory just the write and read structures of this memory starts becoming very expensive. So in-memory compute, without those same components that are doing the storage, be able to do it, this in-memory compute is not a very feasible thing. It's not very, it's not very efficient.
Right. Okay. I do want to get the GSI guys in, but I really think I should let Untether respond to that directly first. Bob, do you have anything from Untether about to reply to GP's criticisms? Or did we lose Bob again? Yeah, I'll be best debate if you really want to let them have their memory architect come and debate with me. Okay, so let's get the GSI guys in on this one. How do you guys see the in-memory versus at-memory difference?
Well, as I mentioned in the talk, the only thing that we're really doing in memory is the logical AND function on the bit line, on the read bit line. So there's not a whole lot more we can do in memory, Boolean wise, beyond that. But that's very powerful for doing the search operations, because we can do, as Dan was saying, we can basically do a match operation to, say, an 8-bit data element on the bit line in one cycle. So it's powerful for search or compare or match type of operations, just the AND function on the bit line. But then we also put a little bit of logic close to the bit line to do other types of Boolean operations, like I mentioned, OR and XOR, so that we can do more complex computations a little more quickly. But there's a balance, there's a trade-off between how much logic we put around the memory cell and how many bit processors we can fit in the array or in the chip. So we could put more, more arithmetic function very close to the read bit line, but then we'll have fewer bit processors, and it will increase the power of each bit processor. So there's trade-off there on how much how much logic it makes sense to put around the put in the bit processor versus.
Sorry, Bob, actually you
Similar.
cannot put a lot of logic there, because if you look at the bit cell is so tiny, you cannot, I mean, we have very hard time compressing even a sense amplifier next to the memory. So it actually doesn't work, I'm sorry.
Well, we have chips, so it does work, but
No.
I mean, you can say it doesn't work, but it does.
It won't line up. I mean, you have to have a sense amp. When you do NAND gate into a memory, that means that you're doing it, putting it before a sense amplifier. That no memory architecture will allow that.
We don't even use the sense amp in our design.
Yeah. So then in that case, you're basically the memory efficiency, the layout efficiency is going to be very low. That's how the memories work.
Yeah, so I think everybody here is trying to trade off, find the right trade-offs between the die area, the efficiency, the compute power that you can offer, and so I think it seems like we've got some different approaches where Ambient is doing all of the compute in the analog domain. And GSI has some compute in the memory array and then some compute outside, and then Untether has the compute very close to the memory array, but clearly outside of it in the digital domain. So Untether, Bob, I see you're back. Did you want to jump in here?
No, I mean, I think the ultimate proof will be, in the deployment and the ability to manufacture at scale, right? We need to be able to make, hundreds and thousands and millions of chips over time. So that's kind of where, things are going to end up. And, it's great to see all the new architectures coming out to solve the AI compute load problem, because it is fundamentally changing the way we're doing compute. And therefore we need to make custom tailored, domain specific architectures in order to be able to address that, growing compute demand.
So, so I want to grab some questions from the audience. There's been a couple of questions from the audience, GP, about as you're working in the analog domain, you're talking about 16-bit, 32-bit precision. There's a question, can you really achieve that level of precision in the analog domain with all the other analog issues? What is the resolution of your ADCs and DACs? So can you talk a little bit more about that?
I mentioned in my, so Linley and everybody else who is asking this question, I have to apologize in advance. The reason is that answer to that question will reveal how that problem gets solved. So I'm not, unfortunately, we live in a world where knowledge is not available as freely as we would think. Right. So I have to apologize in advance. We do achieve, I'll give a hint for experts. As I said, the entire thing we do as a monolithic circuit. You should not see this as an ADC and DAC blocks. As long as you keep seeing them as an ADC and DAC blocks, you will not be able to achieve accuracy. That's as much a hint as I can give you.
Okay, so we're getting into the secret sauce here.
Yes.
All right, so people are very curious about that, but
I know, I'm sorry, but I know this question was asked, has been asked to us at least 1,000 times by now. How can you do 32-bit ADC? And I politely, in most cases, I just smile. This time I have actually answered the question for experts.
So GP, another question from the audience. So you talked a little bit about scaling to future nodes. How far can you take this architecture? And then what is the benefit going to be? Because it seems like at some point, the leakage in these smaller nodes gets to be very high, and it's going to disrupt some of this analog capability.
Linley, actually leakage, let me answer this question in a few. There are many questions in here, so let me answer them. First of all, if 3 nanometer or 2 nanometer was available today and we wanted to scale there, we should have no problem. That's what I believe. We have already done this in 12 nanometer. We have a layout. We have done the circuit characterization. We see no problems at all. From leakage point of view, actually 40 nanometer is the worst technology you can have because it's not metal gate oxide. Right? Once you get to metal gate oxide, the gate becomes even taller and the leakage goes down. That's why from 40 nanometer to 28 nanometer, leakage is actually much smaller. And when you're dealing with this type of analog circuit, there is constant current. Leakage itself is not a big factor.
Right, right. So,
I don't want to steal Akash paper's thunder. So he did ask this question, and I think we have given some answers. Please read his papers to get some more answers into this.
And another question from the audience. And I think this kind of applies to everybody to a certain extent. So GP, you talked about, so you have a custom RISC processor in your design, as well as the Cortex M4. And so did you consider using RISC-V instead of the custom RISC processor?
Yeah, that is simply an application processor. Our technology or processor would make no difference which application processor you use. None of the AI work is done by the application processor, by ARM at all. It's simply just to run application codes. Once an inference has been detected, once some training has been done, then ARM simply orchestrates the application. So yes, we will have no problem using RISC-V or any other processor. In our own engine, AI engine, we could not actually use any of these engines, Linley, because as I explained, matrix is actually a 3D disbursement of variables. And in our case, we introduce yet another variable from our side that your operand can be 4-bit, 8-bit, 16-bit, and 32-bit. And it can change on the fly. What it means is we actually introduced a fourth dimension into the whole equation. So it was not possible to construct this with the existing processors because the best they can really do is SIMD, which is a vector processor. You cannot really make a 2- or 3-dimensional vector instructions. So we had actually no other option than to build our own. The application part, once the AI function has been done, after that the application part can be done by any processor. There is no limitation.
And then the GSI guys, so you guys are using a Synopsys Arc core. Did you guys consider using RISC-V instead of that?
No, not yet. That's because basically of the entire portfolio as a whole, the complex, and not specifically one piece of it.
Right, I see. So kind of the whole package that you get from Synopsys.
Yeah,
That's right.
Okay, yeah, that makes sense. All right, well, we are out of time. So I'd like to thank everyone for participating in this session. Very interesting discussion. And remind the audience that we do have breakout sessions. All of the 3 speakers here will be at the breakout sessions starting immediately. So if you have further questions or you want to hear more about these products, we've got some interesting stuff coming up there. You should have an email with the links to all of the breakout sessions so you can decide which ones to attend. So thanks for our panelists. Thanks for all of you for attending. And this is the last day of our conference, so we hope to see you back again next spring. And in the meantime, please attend the breakout sessions. Thanks, everybody.